山，前方无法跟从，只能引领。中原科技致力于让竹钢走出中国，走向世界。拂袖而走，这世间纷扰尽抛脑后。竹径一直致力于原竹建筑设计施工一体化服务，是原竹建筑行业引领者和领军企业。竹径通过策划和执行全国性大型竹建筑、竹文化活动，特别是原创和惩戒制活动，近5年来完成了200余个原竹建筑作品，原竹建筑案例和市场占有率遥遥领先。举办竹产业、竹建筑、竹文化、绿色发展高峰论坛，全国高校竹建筑设计建造大赛，北林大国际花园建造节，竹建构的无限创造分享会等全国性竹文化、竹建筑活动，以设计加科技赋能传统原竹建筑行业，既传承了传统工匠技艺，又极大推动了原竹建筑行业现代设计和科技进步。风之亭，水之亭，花海竹廊，一山一水，一竹一线，都倾注了匠人的心血。竹径拥有强大的技术研发力量，通过自主研发和与科研院校紧密合作，原竹防腐防霉处理，大幅提升原竹使用寿命。艺术不是建筑在一个伟大的观念上，而是建筑在一个小而诚实的实践上。截至2022年7月，竹径共申请专利30余项，已获得授权发明专利2项，授权实用新型专利11项。竹径掌握原竹建筑连接、支撑、功能拓展等核心技术，赋予原竹建筑全新的造型和美感，在满足功能需求的同时，通过形体塑造，使其与周遭环境融为一体。竹径通过举办全国高校竹建筑设计建造大赛和自主设计，在浙江省安吉县设计和建造了30余个竹建筑，组成了极具中国第一竹乡特色的竹建筑集群，成为泛设计圈追捧的竹建筑探寻之旅特色旅游线路。一枕竹林清风，执竿而渔，无余也乐。
抗变形、不开裂和极具美观的显著特点，密度可达1.2，防腐达1级，防火达 B1级，并具有一定的抗白蚁功能。豪花浆竹集成材广泛运用于地板、门窗、吊顶、背景墙、各种室内装饰、家具制造、体育用品、竹工艺品、日用品制造等各类生活用品制造，材质可与世界名贵木材相媲美。豪花浆竹结构材是公司最新研制的装配式建筑新型环保材料，用作可持续发展的新型竹木建筑新领域。通过实验结果发现，建筑结构材采用集成材最为合适。经过专利技术与现代机械加工后，拥有最佳的极限承载力和弯曲母量，依旧保持着竹材优秀的物理性能，还具有吸水膨胀系数小、不易开裂和不易变形的显著优点。采用公司专利接长设备生产的竖拼竹集成材，可以一次成型10米长、1.2米宽、20毫米厚的大幅面板，支持任意裁切复合，胶合强度高，防腐防霉防火防虫，可用于户外。公司产品已应用于全国很多世界级形象工程项目，如北京冬奥会、鸟巢、行政副中心、雄安新区市民服务中心、天津滨海新区文化中心、深圳张贝郊野公园、福建海峡文化中心、西安奥体中央公园、湖南湘江新区规划展示馆。公司计划未来每年以30%以上速度增长，快速实现上市，为竹材行业发展做出贡献。
熊猫食材到传统工艺，从未有人能将竹完成一次绿色工业化转型，直到竹钢的出现。竹园科技深耕于四川西南有着绿海明珠之称的洪崖县。 洪雅境内竹林资源丰富，以中小劲竹品种瓷竹为主。瓷竹生长快，韧性好，壁脆薄，纤维含量达70%以上。2011年，竹园科技因地制宜发展竹产业，依托中国林科院平台技术，研发而成多竹种重组技术产品竹钢，并将竹钢注册为商标。目前，竹园科技拥有52项专利技术，构建竹产业高科技发展新格局。竹钢高强度竹基纤维复合材料，通过定向重组炼制，竹钢强度可与玻璃钢强度比肩。它耐候性强，阻燃性高，使用寿命长，环保可再生，也能完成锯切、拼接、砂爆、上色、着油漆等多种加工方式，在异形结构建筑应用上有着巨大优势。
正在举行的世园会上，国际竹藤园首次亮相，并且首次使用了一种高性能复合材料竹钢。
通过绿色生态加工工艺制成的竹钢属于负碳产品，已取得森林认证证书，是助力双碳减排、促进绿色发展的高科技重组竹材料。竹钢可塑性强，应用极为广泛，已被应用到建筑结构、景观、地板、门窗、家具、户内外装饰以及装配式建筑等领域。当前，我国要大力发展绿色低碳产业，积极稳妥推进碳达峰、碳中和。竹钢是建筑结构与装饰一体化材料，能为建筑赋予生态竹文化的低碳科技魅力。竹生长期短，容易再生，因此竹钢是以竹代木、以竹代塑新形势下不可或缺的绿色建材。竹园科技不断创造行业的中国标准、世界标准。通过技术创新，我们发明了先进的连续式维管束分离疏解机，建成用于热压生产瓷竹板材的热压机。2021年，经权威机构鉴定，竹园科技竹钢和磨压重组竹地板均实现技术革新，产品达到国际领先水平。竹园科技坚持创新与变革，当前公司正倾力打造包含8县1院1中心在内的竹钢国际生态产业园，其中竹钢板材生产线年产可达6000吨，竹钢户外磨压地板生产线年产可达30万平方米。2022年，竹园科技还投产了竹钢深加工项目，装配式建筑加工也日趋完善。中国式现代化是人与自然和谐共生的现代化。竹园科技推动竹资源创新发展，帮助竹农增产增收。生动践行绿水青山就是金山银山，前方无法跟从，只能引领。竹园科技致力于让竹钢走出中国，走向世界，开创新型竹产业的新纪元。
在这安吉县最具特色的竹建筑集群中，我感受到了归隐山林的静谧，世外桃源的美景。竹林风声起，何处染喧嚣？3、4月采茶踏青，一壶茶酒，拂袖而走。这世间纷扰，尽抛脑后。竹境一直致力于原竹建筑设计施工一体化服务，是原竹建筑行业引领者和领军企业。
竹径通过策划和执行全国性大型竹建筑、竹文化活动，特别是原创和惩戒制活动，近5年来完成了200余个原竹建筑作品，原竹建筑案例和市场占有率遥遥领先。举办竹产业、竹建筑、竹文化、绿色发展高峰论坛，全国高校竹建筑设计建造大赛，北林大国际花园建造节，竹建构的无限创造分享会等全国性竹文化、竹建筑活动，以设计加科技赋能传统原竹建筑行业，既传承了传统工匠技艺，又极大推动了原竹建筑行业现代设计和科技进步。风之亭，水之亭，花海竹廊，一山一水，一竹一线，都倾注了匠人的心血。竹径拥有强大的技术研发力量，通过自主研发和与科研院校紧密合作，原竹防腐防霉处理，大幅提升原竹使用寿命。艺术不是建筑在一个伟大的观念上，而是建筑在一个小而诚实的实践上。截至2022年7月，竹径共申请专利30余项，已获得授权发明专利2项，授权实用新型专利11项。竹径掌握原竹建筑连接、支撑、功能拓展等核心技术，赋予原竹建筑全新的造型和美感。在满足功能需求的同时，通过形体塑造，使其与周遭环境融为一体。竹径通过举办全国高校竹建筑设计建造大赛和自主设计，在浙江省安吉县设计和建造了30余个竹建筑，组成了极具中国第一竹乡特色的竹建筑集群，成为泛设计圈追捧的竹建筑探寻之旅特色旅游线路。一枕竹林清风，执竿而渔，无余也乐。
湖南桃花江竹材科技股份有限公司立足于当地丰富的竹子资源，20多年专注于竹材研发、生产和应用推广，将过去用原生态的楠竹做低端的产品进行了革命性的创新，运用现代技术和机械设备进行大规模生产加工，改变了竹材的原始形态，让平常不起眼的竹子变成了可行销全球的新型高档环保新材料，颠覆了人们对竹材的传统认知。桃花江户外防腐竹材可广泛运用于高端园林景观建设，用作休闲栈道、栏杆、花架、建筑外墙装饰等，极具美观，使用性能远超防腐木和木塑复合材料，具有抗变形、不开裂和极具美观的显著特点，密度可达1.2，防腐达1级，防火达 B1级，并具有一定的抗白蚁功能。桃花江竹集成材广泛运用于地板、门窗、吊顶、背景墙、各种室内装饰、家具制造、体育用品、竹工艺品、日用品制造等各类生活用品制造，材质可与世界名贵木材相媲美。桃花江竹结构材是公司最新研制的装配式建筑新型环保材料，用作可持续发展的新型竹木建筑新领域。通过实验结果发现，建筑结构材采用集成材最为合适。经过专利技术与现代机械加工后，拥有最佳的极限承载力和弯曲母量，依旧保持着竹材优秀的物理性能，还具有吸水膨胀系数小、不易开裂和不易变形的显著优点。采用公司专利接成设备生产的竖拼竹集成材，可以一次成型10米长、1.2米宽、20毫米厚的大幅面板，支持任意裁切复合，胶合强度高，防腐防霉防火防虫，可用于户外。公司产品已应用于全国很多世界级形象工程项目，如北京冬奥会、鸟巢、行政副中心、雄安新区市民服务中心、天津滨海新区文化中心、深圳张贝郊野公园、福建海峡文化中心、西安奥体中央公园、湖南湘江新区规划展示馆。公司计划未来每年以30%以上速度增长，快速实现上市，为竹材行业发展做出贡献。
从熊猫食材到传统工艺，从未有人能将竹完成一次绿色工业化转型，直到竹钢的出现。竹园科技深耕于四川西南有着绿海明珠之称的洪雅县。洪雅境内竹林资源丰富，以中小径竹品种瓷竹为主。瓷竹生长快，韧性好，壁脆薄，纤维含量达70%以上。2011年，竹园科技因地制宜发展竹产业，依托中国林科院平台技术，研发而成多竹种重组技术产品竹钢，并将竹钢注册为商标。目前，竹园科技拥有52项专利技术，构建竹产业高科技发展新格局。竹钢高强度竹基纤维复合材料，通过定向重组炼制，竹钢强度可与玻璃钢强度比肩。它耐候性强，阻燃性高，使用寿命长，环保可再生，也能完成锯切、拼接、砂爆、上色、着油漆等多种加工方式，在异形结构建筑应用上有着巨大优势。
正在举行的世园会上，国际竹藤园首次亮相，并且首次使用了一种高性能复合材料竹钢。
通过绿色生态加工工艺制成的竹钢属于负碳产品，已取得森林认证证书，是助力双碳减排、促进绿色发展的高科技重组竹材料。竹钢可塑性强，应用极为广泛，已被应用到建筑结构、景观、地板、门窗、家具、户内外装饰以及装配式建筑等领域。当前，我国要大力发展绿色低碳产业，积极稳妥推进碳达峰、碳中和。竹钢是建筑结构与装饰一体化材料，能为建筑赋予生态竹文化的低碳科技魅力。竹生长期短，容易再生，因此竹钢是以竹代木、以竹代塑新形势下不可或缺的绿色建材。竹园科技不断创造行业的中国标准、世界标准。通过技术创新，我们发明了先进的连续式维管束分离疏解机，建成用于热压生产瓷竹板材的热压机。2021年，经权威机构鉴定，竹园科技竹钢和磨压重组竹地板均实现技术革新，产品达到国际领先水平。竹园科技坚持创新与变革，当前公司正倾力打造包含8县1院1中心在内的竹钢国际生态产业园，其中竹钢板材生产线年产可达6000吨，竹钢户外磨压地板生产线年产可达30万平方米。2022年，竹园科技还投产了竹钢深加工项目，装配式建筑加工也是日趋完善。中国式现代化是人与自然和谐共生的现代化。竹园科技推动竹资源创新发展，帮助竹农增产增收。生动践行绿水青山就是金山银山，前方无法跟从，只能引领。竹园科技致力于让竹钢走出中国，走向世界，开创新型竹产业的新纪元。 这安吉县最具特色的竹建筑集群中，我感受到了归隐山林的静谧，世外桃源的美景。竹林风声起，何处染喧嚣？3、4月采茶踏青，一壶茶酒，拂袖而走。这世间纷扰，尽抛脑后。竹径一直致力于原竹建筑设计施工一体化服务，是原竹建筑行业引领者和领军企业。竹径通过策划和执行全国性大型竹建筑、竹文化活动，特别是原创和惩戒制活动，近5年来完成了200余个原竹建筑作品，原竹建筑案例和市场占有率遥遥领先。举办竹产业、竹建筑、竹文化、绿色发展高峰论坛，全国高校竹建筑设计建造大赛，北林大国际花园建造节，竹建构的无限创造分享会等全国性竹文化、竹建筑活动，以设计加科技赋能传统原竹建筑行业，既传承了传统工匠技艺，又极大推动了原竹建筑行业现代设计和科技进步。风之亭，水之亭，花海竹廊，一山一水，一竹一线，都倾注了匠人的心血。竹径拥有强大的技术研发力量，通过自主研发和与科研院校紧密合作，原竹防腐防霉处理，大幅提升原竹使用寿命。艺术不是建筑在一个伟大的观念上，而是建筑在一个小而诚实的实践上。截至2022年7月，竹径共申请专利30余项，已获得授权发明专利2项，授权实用新型专利11项。竹径掌握原竹建筑连接、支撑、功能拓展等核心技术，赋予原竹建筑全新的造型和美感。在满足功能需求的同时，通过形体塑造，使其与周遭环境融为一体。竹径通过举办全国高校竹建筑设计建造大赛和自主设计，在浙江省安吉县设计和建造了30余个竹建筑，组成了极具中国第一竹乡特色的竹建筑集群，成为泛设计圈追捧的竹建筑探寻之旅特色旅游线路。一枕竹林清风，执竿而渔，无余也乐。
湖南桃花江竹材科技股份有限公司立足于当地丰富的竹子资源，20多年专注于竹材研发、生产和应用推广，将过去用原生态的楠竹做低端的产品进行了革命性的创新，运用现代技术和机械设备进行大规模生产加工，改变了竹材的原始形态，让平常不起眼的竹子变成了可行销全球的新型高档环保新材料，颠覆了人们对竹材的传统认知。桃花江户外防腐竹材可广泛运用于高端园林景观建设，用作休闲栈道、栏杆、花架、建筑外墙装饰等，极具美观，使用性能远超防腐木和木塑复合材料，具有抗变形、不开裂和极具美观的显著特点，密度可达1.2，防腐达1级，防火达 B1级，并具有一定的抗白蚁功能。桃花江竹集成材广泛运用于地板、门窗、吊顶、背景墙、各种室内装饰、家具制造、体育用品、竹工艺品、日用品制造等各类生活用品制造，材质可与世界名贵木材相媲美。桃花江竹结构材是公司最新研制的装配式建筑新型环保材料，用作可持续发展的新型竹木建筑新领域。通过实验结果发现，建筑结构材采用集成材最为合适。经过专利技术与现代机械加工后，拥有最佳的极限承载力和弯曲母量，依旧保持着竹材优秀的物理性能，还具有吸水膨胀系数小、不易开裂和不易变形的显著优点。采用公司专利接长设备生产的竖拼竹集成材，可以一次成型10米长、1.2米宽、20毫米厚的大幅面板，支持任意裁切复合，胶合强度高，防腐防霉防火防虫，可用于户外。公司产品已应用于全国很多世界级形象工程项目，如北京冬奥会、鸟巢、行政副中心、雄安新区市民服务中心、天津滨海新区文化中心、深圳张贝郊野公园、福建海峡文化中心、西安奥体中央公园、湖南湘江新区规划展示馆。公司计划未来每年以30%以上速度增长，快速实现上市，为竹材行业发展做出贡献。
Okay, I will switch to Mandarin. I really want to thank the organizers for inviting me. I really want to thank the organizers for inviting me and introducing my background. Now, I want to talk about the large span timber structure development and typical connections. I will talk about 4 topics. First, the background. And we know that in China, the structure of wooden products, wooden structures, has a long history, like a Foguangsi, the Easter Pavilion, almost 1,000 years ago, and Yingxian wooden pagoda, also 1,000 years ago, the Forbidden Palace, 600 years ago, grand structure built 1,000 years ago, very tall, very grand, very majestic, a long history. At the time, people did really prefer to use timber to build structures. But of course, later, with the development of building materials, for a period of time, we began to use less timber in structures. But recently, people are valuing the recyclability and structural strength advantages of timber, and it emits oxygen and absorbs CO2 in the growing phase, which became more and more favored by the people. And some people would ask, use timber to build structures. Do you need to cut down the trees? Are you destroying the growth of the trees and back to the environment? No. The trees, once grow to a certain age, it may die. But when you cut it at the prime time and build the buildings and capture carbon in the buildings, create high economic value, then the farmers will have more motivation to grow bigger forest. So you are using the forest to protect the forest, to promote the forest. You're actually making forest a sustainable source. So people know more about wood, and people began to use more large wooden structure. Here, I want to show you gymnasium and very typical structure. 40 years ago in the US, they had a span of 162 meters, Tacoma Dome. And also in 1997, in Japan, they have Odate Jukai Dome, 178 span, and also the speed skating oval from the Olympic Village in Canada, 2008, a span of 100 meters. I'm just showing a few examples. And in recent years, with the enrichment of product portfolio, we not only use raw material or sawn lumber, we actually are using more bigger dimensions, more homogeneous products, more uniformity in the products, providing convenience to the use of timber as a major structural raw materials. We also developed all kinds of steel connectors. So we can use all types of complicated forms and dimensions and connect them very effectively. So you can see we did have a lot of long history, historical heritage. I think large wooden structure in China came at a later date, around the late 1980s, 30 years ago. China and the world began to have a closer contact with each other, and we began to understand the light wood structure and other timber structure used in other countries. We began to build villas or holiday resorts. But mostly in the villa, we don't have a lot of land for villa development, and people want to use timber structure. They want to actually see the wood. They think it's closer to nature and it's visible, and people, especially if we want to have a larger spatial span. Earlier, there wasn't much need for a large span, but now if we want to use them in the public facilities, you want to see and touch the wood because you feel close to nature, especially in public facilities, they need to have a higher, bigger span, longer span. So today I will show you a few real estate auxiliary facilities or the industrial complex auxiliary facility, tourist, gymnasium, conference centers, exhibition centers, etc. I feel that maybe 10 years ago, I'm showing you this tourist visitor center. This was built around 2010. And I think at the time, people began to use more timber. Most residential buildings are reinforced concrete. In some small residential complex, often they would build a wooden harmonious structure for selling the houses. It's like a makeshift house selling unit. This one is very unique by Vanker, a real estate developer. It is not very big, only 2,000 square meters. It's a visitor center. You can see the roof is a wavy form and interior is exposed. Many people, this is the place where they sell the house units. And really, when you see this visitor center, people really began to be attached with this complex. Okay, this is in northeastern part of China. They are using the structural modules and all things are prefabbed. So even in the cold season, they can install and fasten the modules on site despite the low temperature, which is very convenient. And also for building for industrial uses, they use some wooden structure for R&D centers, or warehouses, or employee canteens. So you can see they try to use wood structure. This is in Xuyi. It is a R&D incubator building. Of course, the factory workshops are built by iron and steel, but this is a R&D center built by a hybrid of wood and steel. Another case is Novartis Shanghai. It is a canteen for their employees and a cafeteria where their employees can take a rest and have lunch and meals. The total area is not very big, only 1,000 square meters. It's very attractive. It is an iconic building in the factory complex. And also we have some renovation project in Shanghai, in Yangshupu. Used to be a wharf, but later it was turned into a tourist site and used to be a shipyard. And they are building a venue inside the shipyard, which is turned into a tourist attraction. They're using the wood steel hybridization venue where they can have meetings or exhibitions or art gallery. This is a visitor center in the tourist site. In tourist site, wood is used very frequently. And every year, you will just look into the projects. You will see a lot of tourist sites using timber and steel. And this is in Nanjing Hexi Ecological Hall. It's very beautiful when you look at it from afar. You are using wooden modules and a geothermal heat pump to showcase a healthy building concept and philosophy. This one is a bridge. It's a bridge right beside a station of the Metro Line 16 in Shanghai. When you exit the subway, it's quite boring, right? If you only see concrete walls, concrete buildings, but right beside it, they have a small river and they're building a wooden bridge over it. When you exit this very boring metro station on the ground, you can see immediately this 33-meter span wooden structure, and a lot of people just go there and take pictures and selfies. This is the Haikou Visitor Center in Hainan Island, right in the middle of the Coconut City. And inside this park, you enter this wooden structure. It is in perfect harmony of nearby surroundings. 68 curvy beam. Every beam has a different curvature. The largest span is around 60 meters in perfect harmony with the local surrounding. A very beautiful structure. 9,000 square meters. Some gymnasium. This was an early structure in Chongming indoor swimming pool. I think it was built in 1978, 7 years ago. Only 3,000 square meters. It is a training site, but they're using the steel wood combination, and for the roof structure, the steel is reinforcing the tensile force, and the wooden structure is withstanding the compression force. So when you look at from afar, it's really iconic landmark. And also indoor swimming pool in Rongjiang County of Guizhou Province. Actually, we're seeing many other projects. And yes, I know some are being built, like He International Conference Center or Anhui University Auditorium or some other fine arts academies. So when you actually see this very nature sort of structure, you'll feel refreshed. This is a conference center in Chengdu City. It's actually a huge structure, 400 meters long, 30 meters short, and 25 meters tall. It is a steel timber structure. On the right, I'm showing you a cross section. The main framework is done by steel, and secondary structures are the wood right below the steel roof. Looks really amazing. This is a renovation of an old building, the auditorium of Anhui University, which was built in the 1950s. So they're renovating the roof. And in this process, they maintained the previous wooden structure concept. It used to be truss, some degraded, and now we are using laminated timber. And the structure itself is very beautiful. The construction was finished just very soon, and now it looks really ethereal and really light. This is another botanical garden, 3 domes. 3 domes all together, tens of thousands of square meters. So you display the plants inside the domes. So it's a perfect combination. This is a recent agricultural exhibition garden. It has become a demonstration site for agricultural produce. Also, it can have meetings, conference, altogether 5 pavilions, all use a combination of steel and wood. Largest span is 110 meters. So in summary, the modern wooden structure in China is very short, maybe a bit over 10 years. People didn't really favor it, but now it is extensively used by architects, and people love it. And of course, the forms and shapes and structures are more and more challenging and difficult. So this is really developing fast. Top right, built in 2010. Now, within 10 years, it's already reaching more than 110 meters span. And also for the sliding center of Beijing, its total floor space and 1,900 meters long structure. But of course, there are many issues, structural challenges, basically technical challenges. So first, connection function. For a large span structures, the connecting points are important. So the curving torque and also the bending moment and gravity and the axial forces are exerting influence on them. And you probably need to have all kinds of treatment. And for example, you want to make it easy, but also you want to make it strong. In the middle, for this single shell dome, to make sure that they meet the construction performance, we can have multiple types of connectors. It could be slotted in plates. It could be slotted dovels. It could also be pinched plates or stacked connectors. Okay, for this one, the 3 domes I've shown you before, big domes. So the connectors, we have all types of connectors. And here you can see that here we're using slotted steel plate. And also on the top, we have using a two-way orthogonal connectors.
So they use half-lap joint. This is not standardized joints. So we should understand the features of those connections. And we carried out a series of studies on these. Sometimes we cannot have a real site test. Instead, we can only have a simulation test. We can only have a simulation test. Can you hear me now? Okay. So I listed on this slide some of the tests. This is using the orthogonal joint of members. So double layer main members. There are 2 directions. Through these types of connections and joints test, we can understand their stress and failure models. And by doing so, we can understand their bearing capacity. And through the analysis, we can calculate the stiffness. This is the screw joint with a slotted in steel plate. On the left, you can see this is a slot in and with this wooden base, and also there is a big space between the screw and also the base. And by using this self-tap method, we can closely link the base panel and with the joint. And through the record and the tests, we can understand the failure mode and the bearing capacity. So in summary, we can understand that screw joint with slotted in steel plate has very good ductility, and also the stiffness is very good. And the design is also very safe by applying these types of joint. Because it's a large scale construction, we also need the connections and joints to meet the needs of the stiffness. We use a half lap joint. So what are the features of half lap joint? Again, we use the tests. Understand the bending, tension, and the restriction. We had multiple tests. You can see from the right column, this is the tension test. There are different scenarios to understand the tensils. The top one and the middle one, you can see is adding some restrictions for the bending. And the lower one is adding additional stresses and pressures. Through the scenarios test, we can understand the stiffness and the bearing capacity. Through the test, we can understand their failure modes. Half lap joints have better ductility in axial tension and can satisfy the structure and the functional needs. Another type is also commonly used, called slotted in timber shell joint. Multiple forms. This one in the middle is using the pipe, and the surroundings are the timber bamboo members. And they test different structural bearing capacity, stresses. We compare these different angles, 4 degree, 8 degree, and we tested the stiffness. And through these tests, we can understand the bearing capacity and the stiffness. Through these series of tests, we can describe the flexural deduction process, understand the bending process. So you can see they have very good stiffness. It's just like semi-rigid steels. This is a very popular joint connection. And we can understand their bearing capacity through these tests. My final part is conclusion and outlook. In China, with the emphasis on the green and low carbon development, architects prefer more wood structures. There are diversified wooden structures. There are a lot of large span timber structure being used. From the previous examples, you can see they have diversified modalities and shapes. It's difficult to use one size fits all connection. So we need different types of joints, connections. In order to meet the demand of large span wood structures, we hope we can have further studies on larger joint connections with higher bearing capacity and strong disaster resistance. That would be all. Thank you. Good evening. Can you hear me? I have a question. Professor He. I'm very interested in the Taiyuan Botanical Garden, the connection you showed. During the test, you have the bearing capacity and the stress analysis. Can you show me the result again? Because this is a continuous members. So this is one of the connections for connecting continuous members. You can see this is the screw joint added for this half lap joint. At the very beginning, we believe the stiffness is not good enough. It's not strong enough. And later on, we added additional self-tap screws. And by doing so, we need to test the different sections to finally satisfy stress requirements. I think these types of self-lap and half-lap joints are very useful. There's no error in the processing process. Actually, there's a very stringent requirements for production of such joints. Thank you for your question. Thank you, Professor Yang. If you have any questions, please type your question at the chat box. Actually, we were doing the real engineering projects test based on the size of the members. And we made some tests in the lab. And by doing so, we can carry out the feasibility study. So it's a kind of real test from the field. Thank you, Professor He, for your informative presentation. Next speaker, Professor Yang Huifeng. Can you all hear me? Can you see my shared screen? Yes. Yes. Thank you. Thank you, Professor Lee's kind introduction. I want to thank the organizing committee to invite me for this presentation to brief you about our research result. I will skip this topic slide. This is the outline, 6 parts. The first part is research background. In China, because we have this logging ban on natural forests, so we have to use the high yield, fast growing timber species, but we are still lacking of timber resources. Therefore, in China, those CLT and the pure timber constructed buildings are not so popular because of lack of raw materials and timbers. We borrowed a lot of domestic and international studies, including the timber concrete studies. And we introduced the concrete and to develop this TCC structure, timber concrete composite structure. After the introduction of the concrete, we can enjoy higher stiffness and strength, and it achieved better fire resistance and sound insulation performances, and the vibration comfortability is excellent. This is the background. So our team has been engaged in TCC structures research for 7 to 8 years, including shear connections, including the beams studies. The focus of our study is trying to understand different types of connection and the tensile features. For example, we use different types of screws. We have the Dowel type notch or complex screws. And also in recent time, we had a lot of similar studies on the TCC as well as timber with a steel structure, and some initial results being achieved. In the past 2 years, our studies were based on a master degree student from my university. Now he is studying in Southeast University. And his study focus is on the finite element models for TCC beams. He did a lot of simulations as following from 1-dimensional to 2 to 3-dimensional studies. According to his research, 1-dimensional frame he believes this is good for structure or framework analysis because it's quite straightforward and simple. So this is the 1D frame study, and another one is 2-dimensional beam shell FE model. We have beams plus shells for this two-dimensional model is also good for the structure and framework analysis. The third one is like a solid unit. Of course, there are some steels layers, and through this 3D analysis, we can have higher resolution simulation for the sliding situation and other features like load, deflection, sleep. And he published a lot of papers recently. So this is the first page of the article paper I mentioned. If you are interested in, we can have further discussions. Another background information is for the TCC, the width study of FE is very matured. Why we need to study the effective width of composite beams? Because in application, we should consider different spaces of beams. Because with different spaces, the thickness of the members are different. So a lot of different parameters. And additionally, the joints and connectors are different. So it's very necessary to have further studies with these different types of width. For the TCC, we have two study methods. One is based on the stress. Another is based on stiffness.
So both methods have been tested and studied. And also, we have a test regarding this. For this one, you can see first line, we have TCC specimen code 0.2 to 0.4. And also you have a slab width 0.2 to 0.4. And for the slab width, we have our own forms and dimensions, quite limited. And also we have made a screw diameter test. We had several variations to make a comparative study. This one, from the beam side, we have parameters here, and also the load, deformation, and mid-span stress distribution, especially along the grain, because we want to study after the shear force is exerted. This is a very small chart. We are seeing that this is along the grain. We try to test for that. This is the basic testing rig. And for FE model, we are using a 3D fine FE model. It is good for, we are using solid elements for cohesive elements analysis. We have a model here. And these are the solid modules. And here, the shear, the cohesive elements is very important. If you have a solid element, it is not reasonable, it's not realistic. So here, we are looking at very thin cohesive element to simulate this. By defining the slippage and shear relationship of the cohesive elements to simulate the shear elements. This is a very important treatment. And this one is the spring module. We are using springs along the grain, the length. And also we have some spring power, spring force. So the cohesive elements has a good advantage. It can avoid the load points deformation, because the spring can lead to the deformation of load side to improve the convergence and precision of this model. And this one is a constitutive model. It is an abacus user subroutine. And this subroutine, we can achieve the orthogonal and tensile and compressor studies, stress-strain relation, and plastic multiplier and strength criteria, just some typical feature properties of temper, for example, plastic multiplier. And for this model, we're using Yamada-Sun yield law. We have interlinked flow law to extrapolate the plastic coefficient to define the point damage factor. When the factor is 1, it can be deleted. And then we will delete this point to treat it as a breakage point. And then we are put it in the Fortune language, and we applied for computer program copyright. So now it's a copyrighted program. This one, so basically targeting the simulation, the shear slip model, we are looking at the cohesive elements. We have developed a non-linear cohesive element program still in the abacus. In this subroutine, we describe the shear behavior of the connection. It is an exponential function and also linear for the softening segment. And with fitting of our test experiment, we can get some parameters in the model. And also, this is the reinforced concrete. And also the breakage, cracking of the reinforced concrete. And then we can test the reasonableness and rationality of this beam, and we can simulate the cracking. And this one is the load, the mid-span deflection line. And also there's a comparison with these lines. And the numerical simulation appears to be fitting the experiment curve. And also for the shear lag effect. And we are corresponding to different span length, 0.2, 0.3, and 4. So the press stress reaction at the surface of the slab is diminishing from the center to the nearby surroundings. And also the tensile stress effect is more prominent. From these curves, you can see clearly. This one is that after for the FE span length, we now have a valid data, but this is parameter-based analysis. And for the load type, beta is a kind of effective element coefficient. Beta is a single span. So from this, the load, for the load, the effect is still effective. For example, there's a major deformation for here, that is the beta point load. This is the width to span ratio. This is obvious. Width to span ratio is 0.1 to 1.0, different effect of different load here or here, listed here. So if you have the same width to span ratio, then the loads, 2-point load curves are fitting. It is not corresponding to the absolute width number, but to the ratio. Okay, I will skip the other details. Time is limited. This one is the thickness of concrete slab and effect. And here we have a reinforced concrete. And if we don't have the reinforced rebars, then it will be a major parameter. But also you can see beta decreases with the increase in HC when considering the stress of reinforced bars. And the beta decreases linearly with the increase in thickness. And the curves are nearly parallel under different width to span ratio, representing that influence of thickness, and BC on the effective width might be independent. And this one is the effect on the connection stiffness. And previously, we didn't have a lot of variation of parameters. That could be one situation. And also the height of the beam and the material properties are also tested, but those had a minimal impact on the outcome. So this is the case. Final main conclusion. So fitting analysis using the numerical expression, we use 3 main parameters. Through our analysis, we feel that they're relatively independent to each other. The curves are in parallel, so we multiplied them and we had a comparative study, and the fitting result is really good. Finally, main conclusion. The bending stiffness of the TCC beam increases with the increase of the slab width. And the gamma method, considering the actual full slab width, significantly overestimates the bending stiffness. Owing to the adoption of the user-developed constitutive model of the materials, the FE model shows high agreement with the test results. And some other I talked before. And the main parameter are the width to span ratio, load type, thickness of the concrete slab, and connection stiffness. We published another paper on ES regarding the same study. Effective width of timber concrete composite structures with glued perforated steel plate connections, and also published by our team and some other scholars. Okay, I finished my presentation. I welcome your criticism. I hope I'm not running over time. It's okay, right on time. Thank you very much. So now we actually, for timber concrete, composite beam, and steel composite structure, all kinds what we call modern application of timber structure in China and having great prospect. Okay, let's go to whether the audience has any additional questions. So one question, maybe you can also check, you can also read out. I will switch to Chinese. I hope I can answer this question. Okay, thank you very much for your question. It's a wonderful question. I want to say that this is a good question. Of course, for this composite beam for high-rise wooden structures, multi-story wooden structures, definitely it is anti-seismic, it is anti-shear force, because the bending stiffness of the floor is stronger than the pure wood slab, which means that as a whole, it is increasing the performance. Second question, let me see the English. Can it be connected with, can it be hybridized with the linen fiber or other biomass? It really reminds me, people are putting bamboo fiber into the concrete as a kind of reinforcing fiber. I think it's a very good idea. If you have the biomass in certain user cases, maybe there will be more opportunities, I guess. I think you can definitely try. Okay, thank you very much. For example, we are doing some research on replacing the timber beam with bamboo beam. Yeah, I think it's a good idea to use more biomass. It's a very good idea. I think other questions for TCC come. And also, have you started the long-term creepage or the contraction of the concrete? Yes, it's a very interesting topic, I would say. It's a very good question too. Whether we have the TCC and SCC. Yes, SCC has been developing for quite a while, and the biggest advantage, in my opinion, is a biomass. And also, previously I mentioned this, because in the future, we try to use more biomass. It's good for sustainable development, low carbon society requirements. That is a really good idea. And the second question is that for its long-term performance, we have done some other studies. If you are interested, we'll put in my email box so you can talk to me if you're interested. And we can talk after the meeting. I do have some papers I can forward to you. Yeah, we can share also your materials or paper if you're interested. Thank you so much, Professor Yang, for your excellent sharing and to answer to those questions. Thank you, Professor Yang. Thank you, everyone. So is my sound clear? Yes. Please go ahead. So can you see my screen? Yes, we can see your screen. Thank you very much for your introduction. I thank all the colleagues. I feel very happy to talk to you today, to learn from all of you. So my report is the experimental investigation of dynamic properties of timber concrete composite beams. All your presentation has been very professional. So I sort of follow up on the previous speaker's presentation. And it was a floor vibration study. And this time, I actually focus on the following points. First, the background of the study, and then the purpose, the study itself, key findings and results. So first, the background. Currently, the timber structures are considered to be green, low carbon, and environment friendly. And in the construction sector, it can reduce carbon emission, a very important way. But compared with the reinforced concrete or steel structures, timber has a low density, low elastic modulus. So in the use, it will have annoying vibration or resonance. And also its acoustic performance is not very good. It can transmit noise and sound. And for modern timber floor style, we have 3 types used for example, the joint style, CLT, is mass timber, or TCC. So my presentation is focused on the TCC model. And in my study, I actually reviewed the literature, tried to look at the vibration control indices of timber floor. From the 1960s or till now, many scholars paid attention to the limit states of design. And for the fundamental natural frequency is the key index. And focusing on static limits to control vibration. And later phase, they have dynamic indicators. Now, in all the published meta-analysis, they have some summary, and you can see that most researchers pointed out that the limit states of vibration comfortability and the fundamental natural frequency is the key index. So my study is looking into the natural frequency. I'm looking into TCC. TCC is a structural form that can significantly improve the performance of timber buildings and is mostly used in multi-story and high-rise timber buildings. And steel bar truss slab have been widely used in prefabricated concrete structures, so the dynamic properties of TCC beams using steel bar truss slab were tested and explored. And combined with the theoretical calculation, the influences of connector types and steel bar truss slab in the dynamic properties of composite beams were analyzed, and the comfort level of composite beams and the accuracy of calculation models are evaluated by comparing with existing standards. We actually have 4 testing beams. 2 are shown in the pictures based on the steel truss floor slab, and the other 2 are using ordinary steel bar steel plate. And for the timber beam, for 4800 by 135 by 300 millimeters, slab is 4,800 by 600 by 100 millimeter. And we have 2 types of connection. One is with coach screws. One is based on steel plates. And the slab is steel bar truss slab. And you can see the dimensions and forms of the truss. So this is the push-out test of connectors. This is our test method. We test the connectors first. So we have 2 types, 4 modes of testing. One is steel truss, the other one is plate, and corresponding to direct steel plate and coach screws. Following the EN 26891 testing routines, and we tested pushed out results, and we got the load slip curves. And with the standardized formulation, we have the slip rigidness. You can see that the 2 design configurations, the steel plate, it has high slippage rigidity. And when you have steel truss, the steel plate slippage stiffness is even higher. And for the screw connectors, it doesn't really have an impact on them. The second part is the dynamic test of composite beams. To have a dynamic test. And we have a simple charge supporting system, and we have a velocity sensor. So we have a hammering, pulsar hammering. We can get the signal and analyze and process the signal to get the parameters. And it will get natural vibration frequency, and you can make a calculation. And the next part is to do a theoretical calculation. And under the Eurocode 5, it provides a calculation model for estimating the fundamental natural frequency of TCC beams as shown in the formula. The bending stiffness of EI of the partially composite beams uses the EI equivalent, that is effective bending stiffness based on the gamma method, shown in formula. And Comparison and discussion. The measured natural frequency of the 4 composite beams in the test is between 18 and 23 Hertz.
The measured natural frequency of the 4 composite beams in this test is between 18 to 23 Hertz. So it meets the general requirements of the European standard Eurocode 5 for the natural frequency of the floor system to be greater than 8 Hertz. While it's also suitable for preventing the occurrence of human-induced resonance in the use of the floor and ensure the structural safety. Through this steel bar, you can see we have the reduction of the vibration. We can reduce the specimens vibration and acoustic results. Of course, this is only empirical test result. We need a larger sample to verify the result. Key findings from the perspective of natural vibration frequency, the composite beam used in the test can meet the primary requirements, that is more than 8 Hertz. Secondly, it can be inferred that natural frequency of wood concrete composite beams is closely related to the interface combination. Comparing to the 2 connectors in the composite beam in this test, the sliding stiffness of the planted steel plate connector is greater. So generally speaking, the both composite can satisfy the requirement. However, it's necessary to further compare and study the safety and durability of the 2 connected composite beams in order to give a better choice. Finally, the use of reinforced truss floor deck has a certain influence on the dynamic performance of TCC beams. But whether the effect is significant or not depends on the type of connector. We need a larger number of test samples for verification. That would be all. Thank you. I look forward to the continued discussions and your feedback. Thank you. Thank you, Dr. Wenbo. For your presentation. You talk about the vibration comfort needs and also I want to open the floor. Any questions? If not, let's move to the next speaker. Mr. Tang Yuan, a master degree student in Central South University of Forestry Science and Technology. He will be talking about experimental investigation on long-term performance of FRP glulam UHPC composite beams. Ten minutes. Hi, this is the interpreter speaking. We cannot hear you.
哎，好的，感谢唐元博士刚
Thank
刚
you,
给我
Tang
们介
Yuan,
绍
for your
的关于
excellent
FRP
sharing
胶合木
regarding
UHPC 线性组
FRP
合量长期性能的一
and
些相关的
the
研究。
TOLC
如果后
composite
面的话，我
beam
们
and the long-term
听众区的听众
studies.
有
And
对这个有
later,
兴
if
趣的话， 也
we
可
have
以跟我们
questions,
的唐元博
you
士
can
联系。
contact Tang Yuan directly.
接下来我们就由于时间原因，我们就有请我们下一个
Our next
演讲
speaker,
嘉宾。下一个演讲嘉宾是来自东南大学土木工程学院的
李星浩。
研究生吕星浩。
a third-year graduate study student in
他今天
Southeast
演讲的题目
University
是
of
钢木组
China.
合量长期性能受弯性
The topic
短期
is
受弯性能数值模
numerical
拟研究。
simulation research on long-term
有
and
请吕博士。
short-term flexural performance of steel timber composite beams. Can you see my PowerPoint?
可以。
Yes, please go ahead. Okay, I will start. I will be very short. I know time's already late. 好。 Thank you, Dr. Liu. He talked about the STC long-term and short-term performance numerical simulation. Very detailed explanation. Okay, I don't see any question. Let's go to the next one. From Nanjing Industrial University, Nanjing University of Technology, Wu Tian, Song Xueyi, Song Xue Song, and the topic is the anti-fire and fire retardation improvement of glulam columns sheathed with modified wood. Okay, can you see my PowerPoint? Yes, it's very clear. So good day, everyone. I'm Song Xue Song. I'm from Nanjing Tech University. So my topic is the investigation of fire resistance improvement of glulam columns sheathed with modified wood. I have 4 parts. In recent years, we have shown the burning and combustion of multiple historical structures like National Museum of Brazil in 2018 and Notre Dame Cathedral in 2019. So intrinsically, it is necessary to improve the fire retardant performance of glulam. I'm studying the glulam improvement in order to prevent, to retard fire. So you can see there are several ways to do wood flame retardant modification. Flame retardant coating, they can expand foam, form a dense honeycomb carbon layer. Impregnation modification means the resin reacts with some groups in the wood cell wall material by cross-linking or by filling in lumens, or we can use compression densification. BPF impregnation can improve the dimensional stability, strength, natural durability, and flame retardancy of wood. Compared with the PF, the color of BPF impregnation is lighter, wood aesthetics is better retained, and the residual carbon content and oxygen index are increased. So in our test, we have investigated a combination of PBF impregnation with compression to modify Chinese fir lumbers, which were used as a fireside laminates in glulam columns. So basically, the weight gain rate is 18.4%. The diaphragm of test piece, we have different durations, 1, 2, 3 hours. We are testing 7 pieces. And we are showing the cross-section of glulam columns and thermocouple locations in glulam columns.
Then the effects of different fireproofing treatments on the charring rate and the charring depth of wooden columns and the effects of different fireproofing treatments. This is the test equipment. You can see that we have single-sided fire unless the fire surface is wrapped by refractory cotton binding at 30 centimeters at each end of the wooden column. This is use ISO 834 standard heating curve. You can see the ignition time of column 4 to 7 is significantly delayed. And also the piece 2 is compression and sheath with modified wood, the ignition time is extended to 195 seconds. You can see this is the modified pieces in different ways on the fire resistance of wooden column. The closer the inner part of these members, the longer the time is for fire resistance. We have analyzed the compared group. Compared with glue lamp columns arranged with modified laminates, the temperature of unmodified glue lamp columns rises faster and the temperature peak is high. And again, you can see compared with a glue lamp wood column with BPF, impregnated modified laminate on the exposed surface. The glued wood column with BPF impregnated modified densification board has a shallower charring depth, indicating that the wood density is improved by compression, compacting, and has better flame retardant performance. This is a charring rate. Comparing to the number 3, you can see the BPF impregnation glue lamp columns and BPF impregnation and compression glue lamp columns respectively indicated the charring, lower the charring rate of 18 and 25%. Under the same working conditions, the charring rate of each wooden column at the end of the fire is shown in the figure, which is shown that the two modifications of impregnation and compression can effectively reduce the charring rate. This is the residual bearing capacity test arrangement. Along with the extended firing time, the bearing capacity of unmodified glue lamp columns decreased by 49% when subjected to fire for 1 hour, while the glue lamp columns arranged with single layer of flame retardant modified laminate is between 33% and 39%. It can be seen from the load displacement image that by arranging flame retardant plates on the exposed surface, glue lamp columns can withstand greater pressure and have greater column and displacement. And the stiffness of the member is also improved comparing to the controlled group. With the extension of fire time, the glue lamp columns is more prone to overall instability failure. You can see in duration of a 2-hour experiment, the glue lamp columns covered by BPF impregnation and compression laminates did not have the unstable failure. This is the conclusion. In the interest of time, I won't read all these conclusions. Thank you. Thank you, Dr. Sung, for sharing with us. talking about the fire resistance of modified wood cladding on glulam columns. If you don't have any question, let's move to the next speaker. From Nanjing University of Technology, Mr. Wu Tianyi. Mr. Wu is also engaged on the fire resistance of sheathing light wood structure walls. And he will be talking about experimental investigation into the fire resistant performance of wood frame walls sheathed with gypsum wheat straw composite. I want to thank the organizer for providing me this opportunity to report my research results. Experts, colleagues, good evening. This is my presentation title. 5 parts of my presentation. First, background. In China, we are having this carbon peaking, carbon neutrality, dual carbon goals. Therefore, it's very important and necessary to explore the materials with excellent mechanical properties and fire resistance. I will take the light wood structure wall as the research target and to understand the fire resistance of light wood structure wall. First, I want to understand what's the best preparation process for gypsum wheat straw composite, then residual bearing capacity. In preparation of gypsum particle board, usually we encounter 3 issues. Organic adhesive after fire to produce toxic gas, gypsum crystal structure loose, composite cemented phase. So we have 3 solutions. First is to add inorganic assistant magnesit gel into gypsum to make the crystal of gypsum compact. Second, using wheat straw with high ash content. Third, improvement on the compatibility. Through these 3 factors, 3 levels, we have 9 groups of panels studies. And you can see the results from the analysis of variance and range are highly constant. From this table, you can see that physical and the mechanical properties of the plates prepared by the optimal process are better than similar plates in the current standards. Next, talk about fire endurance experiment. I will talk about LWF wall and LS wall. There are 3 types of constructions: the conventional structure, the new types of structure. This is the double layer plates covered slicing. We use this simulated fire situation, and through this test, we can see the fire resistant limit of a straw gypsum composite wall is significantly better than the normal double layer gypsum board. We summarize the experimental results. Their biggest difference is that for the wheat straw gypsum composite material will initially produce a non-continuous flame, but it will slowly extinguish, will not crack and fall off like gypsum board. Next is the internal temperature test. In the LWF wall, we compare the temperature rise and the resistance limit. We can see that the GB belt can delay the time of wood studs reaching the charring line by 11 minutes. And it can effectively delay the temperature rise rate of wood studs before falling off. When the fireside cover panel becomes double layered, its fire endurance can be effectively extended. And the temperature rise rate of wood studs is greatly reduced. When selecting the wheat straw gypsum composite material, the fire endurance and the charring time and the temperature rise situation all being greatly improved. This is the third type structure. The inner layer is wheat straw gypsum composite material, which greatly improves the fire resistance of the wall and make the charring rate of each stud basically the same. For the LSF wall, the wheat straw gypsum composite material also shows excellent fire resistance. This is the residual load bearing capacity test, which is a kind of axial pressure test of different structural walls and the different fire times. You can see top and bottom wood beam were crushed, fracture of wood studs in plane. You can see the correlation here. Under a 30 minutes duration exposure, the embedded belt can make up for the section loss of the wall caused by the belt, and the residual load bearing capacity was higher than that of a wall with type 1 structure. Likewise, the 60 minutes duration exposure also greatly improved the situation. It is the conclusion. Mechanical properties of gypsum wheat straw composite meet current industry standards and higher than those reported in previous studies. The temperature of LWF wall sheeted with IGW was greatly lower than that of GB wall in fire due to the superior thermal isolation of IGW compared with GB wall. Fire endurance of the wall sheathed with single layer IGW can increase from 82 to 127 minutes. Under 30 minutes duration exposure, you can see the fire exposed panel joints was 21.3% higher than that of the conventional structural wall, and under a 60 minutes duration exposure, the load bearing capacity retention rate was 65.4%. Thank you. Thank you, Mr. Wu. You talk about a new type of sheath materials with gypsum wheat straw composite. which greatly improved the fire resistance performance. If there's no question for him, let's invite next speaker from Southeast University, Dr. Tao Haotian. His research is around timber structures, timber concrete composite structures, and seismic performance of multi-story and high rises. He will be talking about finite element analysis of the connections between timber beam and steel column with screwed-in threaded rods. Mr. Tao. Thank you very much. This is my presentation topic. First, the background. We all know that the most popular connection is bolted timber connection. It has a high efficiency and low cost. However, it has the downsides of low moment resisting stiffness, weak bearing capacity, and expected brittle split failure. Therefore, during the designing phase, we understand it's not applicable in the high rises because it would be prone to seismic shocks. In order to improve the situation, there are some other connections being studied, like GIRs and STRs, glued-in rods and screwed-in threaded rods. But it has the fire resistance and the durability challenges. Comparatively speaking, STRs have better features combined with steel links or steel energy dissipators. It has high withdrawal properties and good seismic performance. And also the lot of FEM simulation. You can see we know that this is a foundation model for bolted connections. So we make these analysis based on the macro level timber models. Because it's too general, then the simulation results is not very good. So there are barely FE studies on GIR or STR connections. Professor Yang Huifeng from my university had carried out a lot of STRs experiments. And we installed the threaded rods and try to strengthen by self-tapping screws. We made the comparisons of different scenarios. You can see. We also checked the load, rotation, loading displacement, and the deformation situation. This is the three-dimensional fine FE model. We use the solid elements, cohesive elements. And we use the special contact properties, hard, normal, friction, tangential interaction. And through these cohesive elements to simulate the withdrawal behavior of STRs. It's also being introduced by Professor Yang.
It can deal with the stress-strain relation, strength criteria, normality rule, plastic multiplier. We also have a steel isotropic, mis-yield criterion, associated flow rule, trilineal kinematic hardening rule, and cyclic void growth ductile damage model. And also, this is programmed in Abaqus user subroutine. The traditional two-dimensional simulation will not work. Sometimes the steel may break while using a cyclic void growth ductile damage rod under the seismic load. Sometimes due to fatigue, the steel may first develop small cracks and ultimately break. This is the cyclic starting criteria for the breakage of the steel component. Based on this breakage and failure model, there have been different studies on different steel strength grade, and we are directly using their parameters in our finite element simulation. Cohesive elements, we are investigating the cyclic shear slip behavior. Hysteric rule pointing to the maximum historical slip, unloading following initial stiffness. This is the non-linear ramp-up stage and the linear descending curve. And also the dissipative load is based on the starting stiffness. We have done the compression and withdrawal study. We get the parameters in the experiment, and then we can do a fitting with our model. Now we can do a comparison and a validation study. First, failure mode. In our experiment, we have non-elastic slippage. By using this cohesive element, we can achieve a non-elastic slippage. Sometimes the rod may break. That is the failure of the cohesive element. And this one, the yield and sectional rupture can be reflected in the plastic elastic model simulation of the steel sections. And then we can see the hysteric curves. When we have the steel connectors, it has a dissipative ability. Then the hysteric curves appears to be thicker and more robust. And considering the limitation boundaries of the finite element simulation is more ideal, then when we are having a cyclic simulation, we need to have a further investigation in order to get a more accurate result. And also in the finite element model, the peak load point is latent than the experiment time point. So we have this mesh. The mesh is thicker than we expected. And also, it is larger than the characteristic parameters, which means that the breakage in the model is later than experimented time for breakage. So there's a latency effect. But generally speaking, this kind of simulation is acceptable. Another thing is the energy dissipation capacity. And the anomalous values in the first three loading stage of CT3 might be caused by the plastic deformation of the washers. And here, the steel connector has yielded the connectors already broke. So the curves later is more flat. And there is a good fitting with experimental value. So the finite element model curves is thicker than experiment, then errors can be expected. Just some conclusions, which I already talked about before, and references. Thank you. Thank you, Dr. Tao, for your excellent presentation. So you have developed a new type of connectors with screwed-in bolts. And you are using a finite element model to accurately simulate its performance. And also you have made many experiments to validate this model. And if we have questions, you can contact Dr. Tao. And the last speaker is from Southeast University, Dr. Liu. And the topic is robust parameter identification for ductile timber connection. His research includes research on seismic performance of self-centering timber structures. Thank you very much. Can you hear me? Yes, we can. So good day, everyone. So I'm talking about robust parameter identification for ductile timber connection. I will speed up my presentation. So application of timber structure. It is a green, low carbon, environment friendly. It is used extensively. I will have introduction of a new type of ductile connection. And very similar to Dr. Hao Tian's presentation, we're using screwed-in threaded rods enter the beam, glulam beam, and then connected through bolts with the box-shaped steel bracket. So we have done a lot of experiments, preliminary tests. We have the mechanical and the screwed-in rod slippage and displacement tests. And also we had some steel link test and connection test. And we have designed a suitable box connector. And this is the box bracket testing results, the form and dimensions. First, the thickness of the plate, and also whether they have the reinforced flange. So this is the failure situation. Usually the breakage, rupture, and yield. And when we have a reinforced flange, then there's a wavy kind of failure. And also you can see the connecting points with a 6 millimeter thickness with or without flange, then they have the same load ability. If it is 8 millimeter, then it has ability to withstand even greater load and minimum displacement. So we are testing with the connection of the wooden beam. You can see that this connector is rupturing earlier than the rupture failure of the wooden beam. And you can using the hysteretic rules, and we can have, we need to have accurate simulation of the performance of the steel structure. And then you can see the hysteretic rules. For every rule, we need to identify more than 10 parameters. And for example, for the number 4, some have 37 parameters, and 4 of them are having clear having physical meaning. And for other parameters, it is very difficult to directly get the physical value. So we need to find other methodologies to identify them value. This is the parameter identification procedure. For example, we have an additional steel link, beam column connection, and multi-scale evaluation. And the code is finished in the MATLAB. And in terms of the methodology for identifying parameters, we were using the scattered method to calculate. But with the single genetic algorithm, the calculation result is too slow, and the result is approximate value in a mathematical sense, but the value is a physical value. So we are using the SVD AOKF algorithm. This is a very good algorithm to deal with a non-linear model. In reality, in multiple iteration, we need to have the array, the matrix, to have interpretation of this matrix. So when the computer is calculating, there will be the error. After several iterations, the approximate errors will accumulate, and the final result may not be accurate. So sometimes the program may break in the middle. We are using exotic value disintegration, and after the disintegration, we can have a stronger and more accurate calculation of the matrix. Then we cannot use the ordinary way to calculate. We are using a method. We are embedding a noise estimation to simulate the covariance of the measurement error. So this one is the results of parameter identification. You can see that the model, the displaced model, is basically fitting the degradation of strength and stiffness. The two curves are fitting. And for energy dissipation, for every stage, seems that the modeled dissipation value is similar to the experimental dissipation value. To better compare the parameters, we are comparing the errors of key parameters. You can see mostly the error is below 10%. So we believe that this is an accurate simulation of the steel connectors. Then the simulated parameters are used in the cross-shaped model. And then we got the key performance parameters, and the error is less than 15%. So the numerical results shows a good agreement with the experimental results, and the stability of the UKF algorithm is improved. The model error of most steel link and connection performance parameters is reduced to less than 10%. Okay, thank you. Thank you, Dr. Liu. So you have talked about new improved calculation algorithm. So if we have any questions for him, we can ask. Okay, I don't see any questions. We have finished today's presentation. And then everyone, we can turn on the camera so we can have a final group photo together. And also, we want to thank 11 scholars and speakers, including students. They shared with us their timber-related structural design and studies. We really want to thank the organizers, INBAR, and they work really hard for providing this academic platform. Okay. Yes. No more to say. It's already very late. Okay, we can open the camera so we can take a group photo in the end. It's like our tradition. Okay, we will ask our colleague to take a screenshot. We want to thank everyone. It is a 1 month long academic session. Every time we have around 100 listeners from all around the world. This time we had more than 1,300 registrants from 800 institutions. So we had waves of audience, basically depending on your interest in certain timber structure topic. Next time, we are talking about engineered bamboo structure. Hope to see you next time. Okay, we also want to thank the translators for providing language translation. Okay, also my colleagues behind the scene too. Yeah, working really hard. It's already very late in Beijing. Okay, thank you, everyone. Okay, let's close the day. Okay. Bye-bye, everyone. Take care. See you next time.